All right, so I guess let's go over this midterm exam for 232. So this first question is just your pretty standard rectangle double integral. We already gave you the bounds. Don't really have to do anything super fancy. So the inner step would be anti-differentiating with respect to y. So I'm going to get this xy cubed over 3 plus x cubed e to the 2y over 2. And then I plug in my y bounds. And so 27/3 is 9. So 9x plus x cubed over 2. When I plug in y equals 3, I get e to the 6th. But then be careful, e to the 0 is 0. So I'll have a -1 right there. And so now I do this integral with respect to x. So 9x squared over 2 plus x to the 4th over 4. Well, 4 times 2 is 8. Sorry about that. So plus x to the 4th over 8 times e to the 6th minus 1 between 0 and 2. So 9 halves times 4 is 18 plus 16/8, so 2 e to the 6th minus 1. So it looks like 16 plus 2 e to the 6th. Okay. Next one, set up bounds for the double integral where D is the triangle with vertices -1, 1, 1, 1, and 0, 0. Okay, and so be careful. This, first of all, is not a rectangle, and therefore the bounds aren't all numbers. So we can immediately rule out, I guess it's this one, right? Not a rectangle, it's a triangle. And then, okay, so for all these others, what else can we do? So if you look at the top and bottom curves, it's not, maybe I'll use a different color for this so I could leave it up. So the bottom curve changes. So that means that dy dx you would need to split it into two pieces. So that rules out this. And so then finally, looks like for dx dy, we're good because the left curve seems to always be, if you figure out the equation of that, that's y equals minus x, so x equals minus y when you solve for x, and then the right curve is x equals y. So basically, look at these, they're pretty close, but be careful when we're doing this, it's for the dx dy ordering. So therefore, we have this. I guess from the very beginning, you could have seen that this is no good, because remember, that for dy dx, you're allowed to have x on the inside bounds. For dx dy, you're allowed to have y on the inside bounds. You're not allowed to have y on the dy bounds for something like that. So yeah, two of those choices are just, well, I guess that one's the worst one because that's not correct for anything. The other one is correct only for a rectangle, and then the others aren't quite right either. So just be careful, draw your picture, and look at all the little details like that. So let D be the region in the xy plane enclosed by these parabolas. Okay, so if we do y equals x squared minus 2, it's just your standard parabola shifted down by 2, and then minus 2x squared plus 1. Well, it's going to be a squished parabola, but then shifted up. So we have something that looks kind of like this, maybe not quite. I guess we need to figure out these intersection points. So if you say, oh yeah, x squared minus 2 equals minus 2x squared plus 1, you'll get that 3x squared equals 3. So this happens at 1, minus 1, you could plug back in, and minus 1, minus 1. Okay, so those are our intersection points. As far as getting it set up, we don't want to do dx dy because for dx dy, the left curve and right curve are sometimes coming from the one parabola, whereas the left curve and the right curve are the other parabola for other values of y. But this one is okay for dy dx because it looks like the bottom curve is always x squared minus 2, and the top curve is minus y equals 2 minus 2x squared plus 1. So our bounds are then going to be minus 1 to 1, x squared minus 2 to minus 2x squared plus 1. And then our integrand is 2x squared y, dy dx. So you get minus 1 to 1, x squared y squared, evaluated between minus 2x squared plus 1 and x squared minus 2. And so squaring that out, we're going to get, what, minus 1 to 1, x squared times 4x to the fourth minus 2x squared plus 1 minus x to the fourth minus 2x squared, oh, sorry, minus 4x squared, right? 2 times each one. So again, I'm writing 2 when I mean to be doing 4, and then plus 4. Let's make that look a little nicer. Okay, and so, oh, and I don't remember what I said, but this should be a 4 as well. Yeah, because 2 times minus 2x squared times 1 gives me that. So those cancel, and I'm left with 3x to the fourth. But then I have this x squared out here, so 3x to the sixth. And then plus 1 minus 4 is minus 3x squared. And so then from here you get, what, 3/7 x to the seventh minus x cubed between minus 1 and 1. So I get, what, 3/7 minus 1 minus, and then at negative 1, we'll have minus 3/7 minus negative 1. So, what, 6/7 minus 2 is negative 8/7. There we go. So let me see here. I might move this all up a little bit. I'm encroaching on the next problem. Maybe not all that. Okay, that's fine. All right, and let's look at this next one. So we give you the bounds. So this is one of the ones where you're supposed to take the hint that you're stuck and that you need to try something else. Because, okay, if I look at this integral that I'm supposed to do, I'm supposed to do the x antiderivative. So the only thing that really would make sense to do would be to let u be x minus x squared over 2 pi, the inside function. But then du is 1 minus x over pi dx, which we don't have. And so, like we've said before, if you can't get a substitution to work out, you should take that as a hint to try either another set of coordinates, like polar, cylindrical, spherical, or something like that, or switch the order of integration. And so, yeah, don't worry about trying integration by parts or anything like that. The idea is that, yeah, we have this inside function, x minus x squared over 2 pi, and we don't seem to have the factor on du that we need to make this substitution work. So really our hope is to try something else. So cylindrical and spherical, those are tools for triple integrals, so that's not going to help us. Polar is really only good when you have circles or disks involved somewhere, and that doesn't seem to be the case here. So really our only hope is to try to get this going dy dx, and see what we can do. So, okay, let's try dy dx. Yeah, okay, so I have a good bit of room. If I go to start drawing this, x equals y squared over pi is a parabola. And I guess y equals pi would be here. If you go through, when y is pi, x is pi, so this intersection point is pi pi. And it's telling us that the left curve is x equals 0, which is the y-axis, and the right curve is x equals y squared over pi, which is that parabola. And so that's that triangle region with the curvy side is, or I guess I should say triangular-ish region, is the region of integration. So that's parabola, y equals x squared over pi on the right side. Okay, so then if we want to get this going dy dx, we have to do bottom and top curves. And so we could solve and get that y is the square root of pi x is the bottom curve, and y equals pi is the top curve. So putting it all together, if we change the region of integration, that's what we get. So 0 to pi, square root of pi x to pi, 2 over pi squared times y times cosine of x minus x squared over 2 pi. Okay, and so I guess we don't know for sure that we're able to finish this, but I at least know that I can do this y antiderivative, because, you know, I just have this y here basically, so that antiderivative is y squared over pi squared cosine of x minus x squared over 2 pi. I'm going to evaluate that between y equals square root of pi x and y equals pi to get 0 to pi. Well, pi squared over pi squared is 1. And then when I plug in square root of pi x, I get pi x over pi squared, which is x over pi, times cosine of x minus x squared over 2 pi dx. And so what do you know? It turns out we are able to finish this off, because this thing that we were missing, this 1 minus x over pi dx, for our substitution that we tried earlier, it wasn't there for the dx dy ordering, but once we switched it to dy dx, the bounds for y sort of came down and gave us exactly what we need. So if we do that substitution now, you basically just get cosine of u du. So the antiderivative is sine of u. And so then I go to plug everything in. So pi minus pi squared over 2 pi is pi minus pi over 2. And then when x is 0, you get 0. So looks like we get 1. So for something like that, if a substitution doesn't seem to get you started, take the hint to try something else. For double integrals, that's either polar or switch the order. And polar is really only good when you see x squared plus y squared somewhere. All right, so I think that was one of the trickier ones. Next one is just a setup. So D is the region in the first quadrant bounded by y equals 0, y equals x, circle of radius 1, circle of radius 2, centered at the origin. So which of these is the correct setup? So this one right here kind of looks like it's on the right track, but it's not, because if you were to do this in dy dx, I'm going to try to draw this circle a little bit better just to better illustrate what happens. And let's do it like that. Notice that dy dx, you'd actually have to split into 3 pieces, because sometimes the bottom curve is the smaller circle. sometimes, and I did a bad job, I should have had this, whatever, I just really need that piece of it. Sometimes the bottom curve is the smaller circle, sometimes the bottom curve is the y-axis, sometimes the top curve is the bigger circle, sometimes the top curve is the line y equals x. So you'd actually have to split this into three pieces. That the region for this picture, for x between 1 and 2, y equals 0 is the bottom, and then the top is the bigger circles. So this region of integration for this choice is actually this trapezoid-ish region where the top part's not a straight line, but in fact a piece of a circle. So anyway, that's not the right region. Okay, so anyway, the presence of these circles is a big hint that polar coordinates are going to be the way to go. And so this one's not quite right because it goes all the way around for theta, and then also the r goes from 1 to 4, but the r value for this circle is 2, so that's out. So then we're left with three choices that have the correct polar bounds when you think about it. That this line is at theta equals pi over 4, this line is at theta equals 0, and then the r values for the circle are 1 to 2. Circles are for 1 to 2. Okay, and then finally it looks like it's going to be this one. So again, make sure you look at all the little details for these choices. This is very close to that one. The only difference is this one is missing the extra factor of r that needs to come in as part of dA. So this is r squared minus r e to the r squared side squared theta once you sub in the appropriate formulas. But that dA, yeah, so this is r squared minus r cosine theta e to the r squared sine squared theta. But then dA is r d theta dr, or dr d theta. It doesn't really matter. I guess we did the choices as dr d theta. But yeah, don't forget that extra r. That's very, very important. It is a small little difference between these two choices, but for something like this where it's not a calculation, we're just asking you to set up, make sure, look at all the little details. And if you notice that two answer choices are very, very close, just ask yourself, wait, which one of these should it be? So anyway, that's that one. What's next? So calculate this, where d is the disk. So this was just a polar calculation that you needed to do. So 0 to 1, 0 to 2 pi, r squared cosine squared theta minus r sine theta, and then r d theta dr once you convert it to polar. So for your theta antiderivative, I guess the intermediate step, remember, is that cosine squared theta is 1/2 plus cosine of 2 theta over 2. So when I take the theta antiderivative, I get, well, this is going to be r cubed times theta over 2 plus sine of 2 theta over 4 minus r squared. Well, the antiderivative of minus sine theta is cosine theta. So after I distribute that r and do the theta antiderivative, that's what I get. So it looks like cosine theta is 2 pi periodic. So when I plug in 2 pi and 0 and subtract, that's going to go away. And then, well, that's going to go away too because sine of 0, sine of 4 pi are 0. So I'm really just left with 0 to 1 of r cubed pi dr. So r to the 4th pi over 4, 0 to 1. So pi over 4 looks like it is. So be careful, periodic antiderivatives cancel out. You could have also realized that this disk has symmetry over the x-axis. And I'm sorry, not the y-axis, the x-axis. And this is odd in y. So those two together, remember our symmetry tricks tell us that that's going to go away. But again, if that's something you don't notice, it's always going to take care of itself when you go to do the theta integration. As long as you're careful, do it correctly. So anyway, that's that. Next one, evaluated this. So pretty much the same kind of thing, except you needed to draw the region. This y equals square root 1 minus x squared is the top curve. Y equals 0 is the bottom curve. So it's really just the first quadrant piece of the previous problem, that x goes from 0 to 1, y goes from 0 to square root of 1 minus x squared. And so that you could play around with to see is the part of a circle. So in polar, this ends up being 0 to 1, 0 to pi over 2, r squared r d theta dr. Don't forget your extra r again. So the reason why this is better is that if you did this dy dx as presented, you'd have 0 to 1 of like x squared square root 1 minus x squared plus square root 1 minus x squared cubed over 3, which that's fine, except you need a trig substitution to do. You'd have to do x equals sine theta, I think. So yeah, if you remember how to do that, that's fine. But the benefit of polar is that it allows you to not have to do that trigonometric substitution. And so anyway, it looks like we get r to the 4th over 4 between 0 and 1 times pi over 2 when you do the theta integration. So what is this? Pi over 8, I guess, is the right answer. Not so bad. So I did that pretty fast, but that should be a very quick integration. All right, so consider a lambda with this density that occupies this disk. Yeah, so I wish I had a little bit more room for this. Let's borrow some from the previous problem. Okay, so first thing to watch out for is this is a disk, not a rectangle. So these choices where it's dy dx and the bounds are numbers, those would be for rectangles. So this one is out, this one is out, this one is out. That, you know, the disk is not equal to the rectangle. So be careful. Bounds are all numbers in x and y, means we're talking about a rectangle. Disk means it's good for polar, so we're on the lookout for those two choices. As far as which one it is, let's take a look. So I know that mass is the double integral of the density. And so if I look at this disk, it's symmetric over the x-axis and symmetric over the y-axis. So the fact that it's symmetric over the y-axis tells me that this term x that's odd with well, I guess maybe I'll write out the steps. So remember, the idea is that this whole integrand isn't odd with respect to anything, but you could split up the double integral of the sum is the sum of the double integrals. And so now, because this integrand is odd in x and we have this symmetry over the y-axis, that integrates to 0. And then the symmetry over the x-axis and that integrand being odd with respect to y means that that integrates to 0. And so the mass really is just 10 times the area of this disk, which the area is pi times the radius squared, so 10 times 4 pi. So 40 pi is the mass. And then that tells us that x bar and y bar are 1 over the mass times the same integral, but x bar has an extra factor of x, and y bar has an extra factor of y. And remember, don't forget to divide by the mass. And so anyway, we didn't make you calculate these all the way out, but essentially that's going to go away from symmetry, that's going to go away from symmetry, that's going to go away from symmetry, and then this is going to go away from the other symmetry. So basically, when you look at these integrals, a lot of those terms are going to go away because you have both flavors of symmetry, and in which case that's going to, once you convert to polar, just leave either x squared or y squared behind, which then, again, with the extra factor of r from dA leads to those expressions. So that was the idea there. This one is pretty much just do the triple integral. You do have to be a little bit careful with the order in which you do things here. So dz doesn't really matter where you put that, but the fact that it looks like the x bounds depend on y tells us that, remember our rule, your variables in your bounds have to sort of be inside relative to which variables are in the bounds. So essentially we just, like I said, it doesn't matter where you do the z, but it will be important to do the x inside of the y, otherwise your answer won't be a number. So we have to do dx before we do dy. Okay, and so looks like the x antiderivative is x squared y squared over 2z, but then I go from x equals 0 to x equals y squared, which gives me y to the 6th over 2z dy dz. And then from here, you can do this however. You could do the separable trick where if I have something like a, b, c, d, f of x, g of y, dy, dx, I'm allowed to do a to b, f of x, dx, times c to d, g of y, dy. So this requires not only your integrand factors, but also your bounds are all numbers, because if you have variables here, that's going to give you variables in your answer, which is nonsense. So anyway, this is going to be like 1/2 times natural log z between 1 and 2 times y to the 7th over 7 between 0 and 2. So what is that? 1/2 natural log 2, because natural log of 1 is 0, times 128 over 7, and so looks like that. All right. Next one, volume below a plane and above the triangle in the xy plane. So let's recall volume. So volume under z equals f of xy and above the xy plane is double integral. That was our first interpretation of double integral, and it was analogous to the Calc 1 interpretation of a regular integral is the area under a curve. Double integral is volume under surface. The other way you could do a volume is by integrating the boring constant function 1. So if I'm asking you to do a volume, you should either be setting up a double integral where the integrand is the surface equation, z equals f, or you're doing a boring triple integral. Whereas if I'm doing a triple integral, that, if you're thinking about it as a volume, it's actually four-dimensional volume, which we don't want to do. Instead, think about this as the mass of a solid E with density given by this integrand. That you have this object that different parts of it are heavier than other parts of it, or lighter, whatever, that's captured by your integrand F. And that's what's going on there. And so anyway, we can immediately rule out these triple integrals where I have an integrand, right? So 10 minus x minus y, that's your density function, and I'm calculating mass. I'm not asking about density, I'm asking about volume. So we can rule those out. And then finally, our region of integration, it says we have above this triangle in the xy plane that looks like this, which first of all is not a rectangle. So that's out, where the bounds are all numbers. Additionally, it's not type 1 because the top curve changes. So dy dx I can't do in a single piece. And so really the only thing that's left is this. And yeah, you can in fact figure out that this is correct. That if you figure out the equation of the left curve, it's x equals y. If you figure out the equation of the right curve, it's x equals 2 minus y. And there we go. So be very careful. Triple integrals, the only time triple integrals calculate volume is if it's the boring constant integrand 1. Otherwise, a triple integral, you want to think of the integrand as density, and you're calculating the mass of a solid object. All right, so then I think the last questions here are just all setup bounds. Yeah, so let's take a look. So T is a solid tetrahedron of the first octant bounded by the coordinate planes, and this thing. So I think we've done several examples like this. You can set two of the variables equal to 0 to figure out these x, y, and z intercepts to help you sketch what's going on. So the part of the plane in the first octant is going to look like that tilted triangle right there. It looks like we're putting dz inside, which means that we're looking for the bottom and top surfaces. So z equals 0, the xy plane, seems to be the bottom surface. And z equals, well, 1 minus x over 4 minus y over 2 is the top surface, right? If you solve for z in this plane equation, that's what you get. So those are our innermost z bounds. So we can scroll down for E and F, 0 to that. And then, okay, our xy bounds are the shadow in the xy plane. And so think about the shadow of this object. That's this triangle. And then it looks like we're given dx dy. So we have to figure out the left curve and the right curve. So the right curve is y equals 2 minus x over 2. Yeah, because the slope is minus 1/2, which means that x is 4 minus 2y. Is our right curve. X equals 0 is our left curve. So that's our C and D, 0 to 4 minus 2y. And then finally, y goes from 0 to 2. That's our outermost bounds. So there we go. Remember, that's the two-step process where first you figure out what's going on as far as for DZ inside, bottom and top surfaces, then you deal with the shadow in the XY plane for the X and Y bounds. All right, next one. Inside a cylinder and inside a sphere. So if you, I don't know, it's going to look something like this, where, yeah, let me see, that doesn't look very spherical. Yeah, draw the sphere first, and then say, okay, well, what part of this sphere is also inside that cylinder? Yeah, you'll get something that looks like that. Okay, so it looks like we're asked to do this in cylindrical coordinates, which means we're still thinking of the bottom and top surfaces. And okay, the bottom and top surfaces are the bottom and top halves of the given sphere. And if we're doing cylindrical coordinates, we have to substitute x is r cosine theta, y is r sine theta everywhere, which basically turns x squared plus y squared into r squared. So our inner z bounds, C and D, are coming from the sphere equation. The shadow in the xy plane is coming from this cylinder, which has radius 2. So the r bounds are just 0 to 2. So it looks like B is 2. And then theta would go 0 to 2 pi, so that's A. So there we go. Okay, and then, okay, it's asking about the volume of the solid. So scrolling back up to what we said a few minutes ago, if you want to do a triple integral to do volume, you just do the integral of dv, but dv in cylindrical coordinates, dv is r dz dr d theta. All right, next one, triple integral x squared. Ooh, sorry about that. Looks like this should have been a triple right there. So above a cone, inside a sphere, and in a half space. So this is sort of half of our ice cream cone shape that we've talked about. So this is sort of what it looks like. And this, we're talking about the y greater than or equal to 0 half of this. So kind of cut it straight down vertically like that, so that if you were to look down in the xy plane, you would just see that shadow. Okay, so we're supposed to set this integral up at spherical. So x squared dv becomes rho cosine theta sine phi squared. dv is rho squared sine phi, d phi, d theta, d rho. And so we could do that. I think that's the very last question. Just get that out of the way. That's a, oh, so yeah, the last part of this. If you do that all out, you'll get rho to the fourth cosine squared theta, psi cubed phi. Nothing too terrible from there. So the y greater than or equal to 0 half, that's going to give us our theta bounds, which are C and D. So theta is going to go 0 to pi, because y has to stay positive. And then so now we have this kind of tricky thing. It's the sphere that gives us information about rho. So our rho is going to start at 0 and stop at 2. So that's 0 to 2 for our rho bounds. And then our phi bounds, phi starts at 0 and stops at whatever it is here. And so remember, it's the cone that tells us about phi. So the intermediate step, you could either just remember that this cone happens to be phi equals pi over 4, or you could remember that z is rho cosine phi, r, which is the square root of x squared plus y squared, is rho sine phi. So you play around with that equation, you get tan phi is 1, so there you go. And so, yeah, our phi bounds are 0 to pi over 4. And then finally, very last question, which of the integrals are equal to this? So this is the bottom top half of x squared plus y squared plus z squared equals 9. This is the bottom half of that same sphere. And then these bounds are the disk, x squared plus y squared less than or equal to 9. So essentially this region of integration is the entire solid ball. X squared plus y squared plus z squared less than or equal to 9. So as far as spherical coordinates goes, that's 0 to 2 pi for theta, 0 to pi for phi. Remember, we don't double count, so that's out. And then 0 to the radius for rho. So those two look good. But then our integrand, square root of x squared plus y squared plus z squared dz dx dy becomes rho squared sine phi d phi d theta d rho, and the order doesn't matter. So it's not this one, it's this one. And then I guess you could also do this with cylindrical coordinates, where this becomes the square root of x squared, well, sorry, x squared plus y squared is r squared. And then dv is r dz d theta dr. So it wouldn't be this. And if you think cylindrical, the bottom half of the sphere is r equals minus square root of 9 minus r squared. The top half is z equals positive square root of 9 minus r squared. So that's the other one. So note there are multiple answers to this. It's those two. All right, so hopefully that clears up any mistakes you made. If you have other questions on this, let me know. But I will see you later.